Hi, welcome to EE16B. My name is Sid,
And I'm Savan.
and today we're going to do linearization. Specifically, we're going to talk about linearization of systems. And in order to build up to that, we're going to describe what linearization is in general, and we're going to start with the simplest case. So a linearization of a one-dimensional function. So that's a function from real numbers to real numbers.
Right. So we can graph this, right? It would look something like this. Just x, f of x, and it's some complicated function.
Yeah. Cool. So I couldn't have drawn a better function, Savan. Good job.
Thanks.
Okay, so we're going to try and achieve linearization. So if you look at the function like this, it might be really hard to figure out what's going on generally. So we're going to try and restrict ourselves to a small region about a point. Let's say we're going to call it x0.
x0. Just
Cool.
Put it right here.
So can you mark f of x0 too?
Yeah. So
Awesome.
x0 is here, and then f of x0, if I can draw a straight line, is here.
Cool. So we're going to try and create an approximation of the function f about this point, basically. And we're going to do that using derivatives. Cool. So Savan, what's the definition of a derivative with respect to limits?
Yeah. So throwing back to high school calculus, let's see, df dx evaluated at x naught was something like this, right? It was a limit as x approached x naught of f of x minus f of x naught over x minus x naught, right? As this x approached x naught, this became the limit.
Cool. And if you remember what the derivative means graphically, this derivative refers to this line or the slope of the curve at that point. Now, if I can draw straight.
Let's use a different color.
Okay, let's do it in color. Awesome.
Yeah, so this orange line represents the derivative at that point.
And furthermore, if you look at it, it kind of looks like around this point, this line actually approximates the function pretty well. And that's what we're going to use. So let's say, if I can change back colors on time. So let's say df over dx evaluated at x0, this is just different notation for this, is approximately equal to f of x minus f of x0 times x minus x0, where orange. This x belongs to, oh no, wrong color. Let's pick orange. Orange. Okay, so where this x sort of belongs to this neighborhood, that small neighborhood about the point x0, that sort of maps onto this point, where the approximation is pretty good. So Savan, right now over here, I've drawn this small neighborhood thingy. How do I determine what's a valid neighborhood?
Well, a valid neighborhood would be where the derivative doesn't change very fast, right? Where it looks fairly linear. So you could say, like, if you had a graph of a function that looked something like this, trying to linearize about this middle point would be bad. So this derivative is very different. Let's use a different color 1 second. This derivative is very different from this derivative, which is very different from this derivative. And it's pretty hard to say that a linear approximation is valid. So this is bad. But if you had something like, I don't know, something fairly straight or straight-ish, or smooth would be another way of saying it, right? So like an exponential, e to the x. Then you can see that a linear approximation isn't horrible. Like, as long as you stay within a fairly close region, and it's a good approximation.
Exactly. And we can also pick our points x0 such that the corresponding region in f of x, the derivative and the function itself, the slope and the function itself line up pretty well.
Okay.
Cool.
So how do we do that?
So we're going to try and exploit, we're going to basically use this equation up here, where within this neighborhood that we're talking about, the df of dx evaluated at x0 is approximately equal to this thing. So we're going to change colors to purple, and going to take this term to this side, and then bring this term to this side as well. So doing that, we get f of x is approximately equal to f of x0 plus df over dx evaluated at x0 times x minus x0. Cool. Now, looking at this function, I'm going to change colors one more time. Savin, what color do you want?
Blue.
Blue. Light blue or dark blue?
Light blue.
Light blue. Fun fact, light blue is the color of the sky, and Savin's name means sky.
And it's also the color of my shirt.
Good job, Blue. Okay. So we're going to look at this in particular. Note that this is a constant. This is also a constant, and so is this. So if I just do some algebra, this whole thing basically simplifies to something of the form f of x is equal to mx plus c. Whoops, that doesn't look like a c. Mx plus c, where m is df over dx evaluated at x0, and c is a combination of this, this, and this. This is an equation of a line, which tells us that, more specifically, it's the equation of this line right here. And within this neighborhood, we can essentially consider a function to be this line. Cool. We have linearized our function. Great. Now that, so, we have studied the linearization of functions of the form f from R to R. So one-dimensional functions that taken as input real numbers and output real numbers. So now we're going to up the ante a little bit and consider functions that take as input n-dimensional vectors. So we're going to consider functions of the form Rn to R. Now, as you can imagine, functions, this would require the generalization of a derivative of some sort. So before we get to that, Savin, can you write down what the linearization of a one-dimensional function is? In
so
this form?
Just from what we wrote down before, right?
Yeah.
We just had f of x equals f of x naught plus df dx times x minus x naught, right?
Cool. So we're going to evaluate it at x0.
Sorry, yes.
Yeah. So, cool. So don't forget to do that in the exam, by the way, because if you just take the derivative, this is still going to be a function of, potentially might be a function of x, and that will get confusing.
Yes.
Cool. So now, let's, what do you think if x is a vector instead,
Right.
what do you think the form's going to look like?
Well, presumably it would take the same form, right?
Well, something
So,
similar. Yeah.
I guess the f of x would just be f of the vector x, right? Where x, the vector, is, x1, x2, all the way to xn, right? Something like that. So f of the vector x equals f of, x naught vector plus generalized derivative, which is the gradient of f evaluated at x naught times x minus x naught. And when I say times, I mean the dot product.
Awesome. So this is an n-dimensional vector, and so is this. So we're going to write down what the form of the gradient is in blue color. Okay, so let's write down what this function is. So the gradient of a function, which is, the gradient is basically the generalization of a derivative of functions of this form. This is defined as follows. This is going to be an n-dimensional vector.
This x is a vector, right?
Yeah,
Yeah.
sorry about that. So as you can see here, x is equal to x1, x2, and xn. So the gradient of f as a function of x is defined, the vector x is defined as follows. It is partial df over dx1, partial of f with respect to x2, dot, 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 partial of f with respect to xn, and these would be evaluated at the vector x.
Because these are all necessarily functions of xn, right?
Yeah.
Okay.
So one thing to note, this evaluation, just because we're taking the partial with respect to x1, this evaluation is not simply at x1. This evaluation is at x1, at x2, at x3, dot, 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 xn.
Yeah.
Cool. So Savan, can you remind us what partials are? Like, how do we take partials? So say if we had a function that looked like f of x1, x2 plus x3. What would the partial with respect to x1 be?
Oh, we take the partial derivative by taking the derivative of the function as we normally would, and then just treating the other functions, other variables as constants.
Exactly.
So df dx1, we treat x2 and x3 as constants.
Okay.
So the x2 would remain, this would go away, and the x3 would go away.
Okay. And what's it with respect to x2?
And then df dx2, similarly, is just x1.
And with respect to x3?
Just 1.
Cool. So if you're working in this three-dimensional space and this was a function f, the gradient of f as a function of x is going to be equal to x2 from this term, x1 from this term, and 1. Note that these are functions of x1 and x2, and if we want to linearize it, we would need to evaluate it at a certain point. So if you were evaluating it at x1 is equal to 0, x2 is equal to 0, and x3 is equal to 0, for example, evaluating it at these points tells us that, let's say all of this is x0. This tells us that this of x0 would be 0, 0, and 1. Cool. Now we're going to go to the multi-dimensional. We're going to
Generalize
generalize it one step further. Cool. So now we've studied functions of the form f from R to R, and this somewhat looks like f of x is equal to f of x0 plus df over dx evaluated at x0 times x minus x0. We study functions of the form f from Rn to R, and this somewhat looks like f of x is equal to f of x0 plus the gradient of f evaluated at x0 dot product with x minus x0.
Where all of those are vectors?
Yeah.
Right.
I keep forgetting the vector symbol because you just tend to lose them after a while. Cool. And now we're going to consider functions of the form f of Rn to Rm. So how we're going to tackle this is to try and reduce this case to something that looks somewhat like this case. And this is legit math notation for somewhat, a really squiggly line. I'm just kidding. Don't listen to me. So we're going to try and break this function down into something that looks like this. So, Savan, how do you think we're going to do that?
Well, if the input's a vector and the output's a vector, why don't we just break apart the output vector into its constituent parts?
I like that. So, just to reiterate, this is x, an m-dimensional vector, and this is going to be n-dimensional vector, pardon me, and this is f of x, which is going to be an m-dimensional vector.
Where f is also a vector.
Yeah, but that's bad notation. Sure. Okay, so we're going to break up f of x. I'm just going to erase this away so that we have more space. I'm going to break f of x into so-called coordinate functions. I don't know if it's actually called that, but that's what I call them myself. So like f of f1 of x, f2 of x, dot, 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 fm of x. So note that each one of these functions, if I'm just going to change color really quickly, this one function is a function from Rn all the way to R, which kind of makes it look like this thing. And that's exactly what we're going to use. So Salvin, try to, let's just say, try to use this fact and guess what we put over here to try and construct a linear approximate.
Okay. So I guess what we would probably take is the, let's move back to red.
Okay.
So what it would probably look like is basically we can just do this first part to each individual part. So I guess this would be F1 of, just copying from up here. Let's call this x0 naught plus the gradient of F1 evaluated at x naught dot product with x minus x naught.
Bingo. Cool. So now we can do it for the rest. So F2, Fm, x0 plus delta F2 Fm. I don't know if like writing things vertically is faster, but when I was a wee young laddie or lad, I don't even really know. I used to think so I still believe that. Anyway, moving on. So, if you look at this, we're gonna this is the correct answer, but we can try and simplify it a little bit to basically try and get some structure from it.
Yeah.
So we're gonna try and simplify this a little bit. The first thing to note is that this section, let me just change colors really quickly. This section right here looks like a vector on its own, where it's separated from this section by a plus sign. So we're going to try and exploit that. So what we're going to do is we're going to do some magic. I'm going to put this right here. If I can draw clearly, we're going to put this right here and separate this out, and then put a single plus sign in the middle. Cool. So now this somewhat looks like this term, this somewhat looks like this term. Now, if you notice, this over here and this over here looks same but different, right? Now we can try and expand what this thing is going to be. So this part looks like a vector that looks like this, dot product with a vector that looks like this. So this is this is that. This part multiplied with this looks like this just gets pattern matched to that. Since this is going to be the second coordinate, we're going to bring this down here. Likewise, whatever's over here, we can bring it over here, so on, and what's over here is going to look over here. But wait, these are basically just a bunch of rows.
So it looks like a matrix, right?
It looks like a matrix. Completely coincidental. Not planned out at all. Okay, we're going to use that now. And we're going to do that. And I'm going to edit this for lack of space and because I really like the flames. In fact, I'm going to add something to it right now. Fire. Okay, I'm going to okay, try hard humor, the best kind. Okay, I'm going to reduce this to the matrix form. I'm going to erase some of this, and I'm going to try and exploit what we had earlier. So let's forget the matrix for now, and just put some space over here. I can erase this in time. There's going to be, we know there's going to be some matrix over here, and there's going to be some vector over here, right? So this vector in this space over here is this vector. So I'm just going to write it in horrible notation as x minus x0.
Cool.
Now, as we mentioned earlier, this row is going to be f1 evaluated at x0. The next row is going to be f2 evaluated at x0, dot, dot, dot. The next row is going to be fm evaluated at x0. So Salvin, what's this dimension?
Well, these are an x naught is an n-dimensional vector, so the gradient of it should be, well,
N-dimensional.
Yeah.
Yeah. No.
Sorry, I meant n-dimensional.
Yeah.
That's what I said, n.
N-dimensional. Cool. And then likewise, this one, since the output over here is m, you'd expect this to be m-dimensional. Always check your dimensions. If there's one thing in 16b you should take away from the linear algebra part is check your dimensions. Cool. So now we have a generalization on how to linearize functions of this form. And now we're going to apply it to systems. Woohoo! Awesome. Awesome. Now we're going to try and use what we've learned so far in order to linearize systems. So really quickly, when we talk about systems, what we mean is, we usually mean something of the form like this. So x dot is equal to f of x comma u. This is a loaded expression. So x is going to be our state space vectors. And this is going to be, say, n-dimensional, n for nougat. Cool. Awesome. U is going to be our m-dimensional vector, which represents our input. And say, let it be m dimension for m for mammoth.
So m-dimensional.
M-dimensional. Mammoth dimension.
So this is n-dimensional.
Nougat dimension. Is there an animal that starts with n?
Probably.
We're blanking out. We're really tired. Okay. F is going to be our system function. So, an important thing to note is that when we put something in this form, we're trying to model a real-world system to be a function that takes in the current state at a particular moment in time, along with the current input, and outputs the change of state at that particular instant with respect to time. So implicitly, x, u, and x dot are functions of time, but because we're considering f to be a function of x and u, we're only going to consider x and u at a particular time to see what the change is at that particular time. So we pretend x, u, and x dot are kind of like constants for now, but we'll elaborate more on that a little later.
Right. So we just ignore the fact that they're functions of time when we try to linearize it.
Yeah.
And then we put back in that they're time variability when we actually start looking at how the state evolves with time.
Exactly. So to really like summarize it in one go, when we linearize f, we are linearizing with respect to x and u, which are implicitly functions of time, but we don't care about that.
Yeah.
Sound good?
Sounds
Cool.
good.
Okay, so let's now try and linearize this f, our system function with respect to x and u. So we have, keeping with what we have last time, we have f of x comma u is equal to f of, what do you want the initial states to be?
Say x naught and u naught.
Sounds good. Convention is Bayvention. Okay. Plus some, like the generalization of the derivative that we talked about last time. It's colloquially, it's often called a Jacobian, and we take the Jacobian with respect to, the Jacobian refers to that matrix that consists of the gradients along its rows that we mentioned earlier. So we're going to call the Jacobian df of dx, which is basically, someone elaborated on this earlier, but this is basically the generalization of the derivative with respect to x, evaluated at x0 comma u0 times x minus x0 plus the Jacobian with respect to u, evaluated at x0 comma u0 times u minus u0. So, can you elaborate on what this and this is? With a new color, if possible.
Yeah, let's. So what's going on is that these are just the Jacobian matrices, as Sid mentioned, and they're the partial derivatives that we were talking about before, right? So, I like to use this notation, but this is sort of not the best. It just shows that this is the gradient with respect to x of f and all of the x functions.
Gradient, but not really.
Not quite the gradient. generalized gradient. So what we have here is we have dx df1 of x naught comma u naught in the first row, dx df2 of x naught u naught in the second row, and it keeps going down until we hit the gradient of x of f n x naught u naught, because this is an n-dimensional vector, n-dimensional. So if we actually evaluated this out, it would be like df1 dx1 of x naught u naught df2 df1 dx2 of x naught u naught df1 of dx3 of x naught u naught,
and so on.
and so on. And then similarly, this would be df2 of dx1, df2 of dx2, and this matrix continues.
Cool. So this, one way to easily figure out the dimensions of what you expected your Jacobian to be is to note that in this case, this is n-dimensional, and your output is also n-dimensional. This tells us that this thing should be an n by n-dimensional matrix. We construct a Jacobian with respect to u in a similar way. So this would be, this thing would be something like to use Savant's notation with respect to u of x0, u0, with respect to u of f2, comma x0, u0, and so on. And since the input is going to be m dimension and the output is going to be n dimensional, you expect this to be an n by m dimensional matrix, which kind of makes sense, right?
Yeah.
Cool. So one thing just to remind you, what we mean by f1 and f2, like over here, is that we're saying that this function, let me change colors. This function f, we can break it up into, the colors didn't change, GG. So we can break it up into basically the coordinate function. So f1 of x comma u, f2 of x comma u, and so on, fn of x comma u, to be this kind of matrix. Sound good?
That's good.
Cool. So now, 7. Why are they... This looks kind of like what we've done so far, but the difference is there are two derivatives here, like one over here and one over here. What does that make sense?
Well, it's kind of like the chain rule almost, right?
No. Let's start it again. Just literally says the change of this and the change of this, and we kind of need to add the changes together. It's not the chain rule whatsoever.
Fine. Anyways.
Sorry. It's kind of like if you were to keep x constant, the linearization would be...
Okay, so it's like taking the partial with respect to one plus
Yeah.
the partial with respect to the other. Okay.
Pretty much. Okay.
Fine.
Oh, actually, let me just erase this part. So 7, unlike this whole expression looks similar to what we have last time. But why are there two of these over here? That kind of doesn't make sense to me.
Well, you can kind of think of them as x and u are pretty much separate from each other, right? X is not connected to u. So we can take the derivatives of both of them separately and break it apart into the sum of the two derivatives. So it's easier to look at and easier to evaluate.
So exactly. Another way of thinking about it is if you were to keep x completely constant, you can construct a linearization of f, constant x and u, and then you'd get this term. Likewise, if you kept u constant, you could construct a linearization with respect to x, and you'd get this term. But since x and u are independent of each other, when you combine them, you get a linearization of this form, which is why there are two terms. Cool. Now we're gonna try and use this linear approximation to make this simpler. Awesome, great. So now we're going to use that to linearize our system. And this is where things get a little complicated. So f takes the state space as the input. So 2f, all fc's is the current state, or like the state as a function of time, and u, and the input u. But underlying everything is that we are sort of progressing in time, and f outputs the change of the state space with respect to time. So when we linearize our system, so when this expression here, we have linearized with respect to x and u, so our states. But x and u themselves are functions of time, and we're not linearizing with respect to time. Does that somewhat make sense?
That makes sense.
Cool. Okay, so here's probably one of the tricky parts. So let's say, I'm going to change colors. Blue is good. So let's say x, our state, is equal to x0, like our ideal state, plus delta x, which is a deviation from the state. Okay? An important thing to note is that x, x0, and delta x are functions of time. But but with respect to the system function does not care about time because we're trying to abstract away time since the system is only a function of the current state and the current input. Cool?
So you could say that the system is time invariant, right?
Not necessarily.
God damn it.
Sorry. Okay, so now we're going to look at this term and try and interpret what it means. So we have a system function that takes as input the ideal state vector, which is also a function of time, remember, and the ideal input, which is also a function of time. So Savin, what do you think the output's going to be?
Well, this just matches pretty well to this, right? So it should be just a derivative.
Yeah, exactly. So f as a function of the ideal input and the ideal state space would give us how the ideal state space changes as a function of time. So this would be x0 dot. So the derivative of x0 as a function of time. Sound good?
Sounds good. So
Cool.
just something about notation. You'll notice that we use a lot of df dx's and df du's. If you see a dot above it, that specifically means it's a derivative with respect to time.
Exactly.
If we mean a derivative with respect to anything else, we will write out the full derivative like that.
Sounds good.
So this is d dt of x.
Yeah. Cool. Now, we're going to do some simple algebra here, and from this thing and this thing, we're going to conclude that this is equal to delta x. And remember, this is also a function of time. And now we're going to say u is equal to u0 plus delta u, where these are functions of time as well. And then this becomes delta u. Sound good?
Sounds good.
Okay. So now we've basically reduced this to x0 dot plus df, partial df over dx, which is just a notation for the Jacobian, times x0 u0 times delta x plus df over du times x0 u0 times delta u. Cool?
Cool.
Okay, now we're going to try and break this one apart. So this is f of x0 plus delta x times u0 plus delta u, where we've plugged in this x, this u, and that u. So Salvin, on a high level, what do you think this means?
It looks really close to a small change from it, right? Like a derivative almost.
Yeah. So, roughly speaking, f takes in the state space plus a small deviation, the ideal input plus a small deviation, and connecting it to this equation up here, what we're going to get is the ideal change, dot, plus the small change that comes because of these parts, which is equal to delta x dot. So remember, delta x is also a function of time, which is why this makes sense. So f, a system function, takes in our ideal input, our ideal state space, ideal input, and the small deviations, and then we get out the ideal change plus the change because of the deviations. Sound good?
Sounds good.
Okay, so now I'm going to plug this back in, like, I'm going to replace this thing with this thing, and I'm going to get, so erasing stuff away. This is equal to x0 dot plus delta x dot. Now, happy days, we can cancel these two.
Great.
So now we have delta x dot is equal to df over dx times x0 comma u0 times delta x plus df by du at x0 comma u0 times delta u. So as you remember, this is a matrix which you're going to call A. This is another matrix which you're going to call B. And now we have our nice system equation, delta x dot is equal to A delta x plus B delta u, which is our linearized system.
Great.
Note that we're not working with x. When we solve this equation, we're not working with x exactly, but we're working with these deviations, which is a slight difference. We sort of changed our state space variables.
Mm-hmm.
Cool. Now we're going to try and do an example of what we've just done. So let's say we have a system that's of the form. Simon, what color do you want?
Let's do maroon.
Okay. So let's say we have a system of the form x dot is equal to f of x. So there's no input. And we have f1 of x is equal to x1, x2 plus x2 squared. And f2 of x is equal to x1 plus x2 plus e to the x1. Extremely contrived. Okay, so we have x. What we mean by x, just to clarify, is this vector, x1 and x2, and f of x is equal to f1 of x and f2 of x. Sound good?
Cool.
So let's linearize about the point x1. Let's put a 0 on top to denote that we're doing it around that point. Let's say this is equal to 0 and x2 is this is equal to 0. So note that these are also functions of time. The only difference is, so what a 0 function is that no matter what the input is, the output is 0.
Right.
So
And
7.
These could also all be functions of time too, right?
x1 and x2 are functions of time.
Yeah.
Yeah. Cool. So 7, how would you go about linearizing about this point?
Well, first thing is we have to find the Jacobian matrices, right?
Mm-hmm.
So for 2 by 2, it would look like this, right? So we say df dx is the following. So this would just be df1 dx1 and df1 dx2 df2 dx1 and then df2 dx2.
Mm-hmm.
So just doing this out. So df1 dx1 is just x2.
Mm-hmm.
Df1 dx2 is x1 plus 2x2.
Mm-hmm.
df2 dx1 is, let's see, that's just 1 plus e to the x1.
Mm-hmm.
And then finally, df2 dx2 is just 1.
Cool. So now we need to evaluate it at the starting conditions, and what is that?
Right. So the Jacobian evaluated at 0.
Comma 0.
0, comma 0.
Yeah.
Right. Yes. At 0, comma 0. is just, well, this goes to 0, 0, 1. Sorry, this should be 2, not 1.
Yeah.
2, 1.
Mm-hmm.
Nifty.
Nifty. I like that one. Nifty. So now we have, basically, once we do this, we have our linearized system model, which is basically our delta x dot is equal to 0, 0, 2, 1 times delta x. And we're done.
And we're done?
Yeah. So how we get to it is kind of complicated, but basically what it boils down to is finding the Jacobian and realizing that when you're linearizing about a point, we're working with deviations from that point. That's the main goal of linearization. How we get there is rather complicated, and yeah. What are you doing? Nice. Hey. Okay, let me add something else before we leave. If you want to turn off the video now, you may do so, but I don't know what I'm going to add now. Now I'm putting too much pressure on myself. I'm not going to do anything. Bye-bye.